So, welcome everybody to today's seminar. It's a great pleasure to have the speaker, Professor Yariv Kafri from Technion, Israel Institute of Technology, Haifa, Israel. So, this webinar series on statistical mechanics is being organized through the Visitor Associates and Students Program at the SN National Center for Basic Sciences, Kolkata. Professor Yariv Kafri is the Lido Chair in Solid State Physics at the Technion. His research is focused on statistical mechanics and its applications concerning systems which are far from equilibrium and which often display striking and dynamical and collective behaviors which are usually not observed in equilibrium. So his research interest spans a wide range of topics like non-equilibrium fluctuations, molecular motors, translocation of polymers, conformations of DNA molecules, chemotaxis of bacteria, target location by proteins, physics of vortices, etc. And recently he has been working on active matter systems and driven diffusive systems. Indeed, he has contributed immensely in problems of characterizing large-scale structures, dynamical phase transitions, and large deviations in such systems. And especially to the students who are present here. So Yariv is an excellent teacher. Indeed, the students who have attended the lectures in some of the recent schools already know this. So students, please feel free to ask questions whenever you think you do not understand or have any doubts. So now I would like to invite Yariv to deliver his talk. Yariv, please.
Okay, thank you very much for the very kind introduction, and it's a pleasure to see some old friends. And again, I can't see the faces, so please stop me whenever you feel you have a question. So today I'm going to talk about the long-range influence of disorder on active systems. This is work that was done by a host of people, and specifically people in the Technion and outside the Technion. And I've highlighted the two works that I'm going to focus about, which you can find the references below. And the authors there are Idan Bendo, who is a PhD student who's graduating soon at Technion, Sungan Ru, who is a postdoc here, and Julian Tayor from Paris, and Meron Kardar from Boston. Okay, so before I tell you about the influence of disorder, I want to introduce active systems. I'm sure that many of you have heard about them, but just to be safe, I'll give a very brief introduction. So active systems are a class of non-equilibrium systems, where each particle consumes and dissipates energy in order to generate motion. So in contrast to driving a system, for example, through the boundaries by a chemical potential difference, here each microscopic degree of freedom is consuming energy and dissipating it into the environment in order to self-propel itself. So there are many motivations for studying active systems. The first ones were actually biological, and I'm giving a simple example here of E. coli bacteria. So E. coli bacteria are about a micron in size, and what I'm showing you is a really old movie from the Howard Berg lab. And if you track the E. coli bacteria, you'll notice that their motion is roughly such that they move in straight lines for about a second. And once every second, they stop, choose a new direction, and move in the new direction. And that's called a tumble. So this motion of running, choosing a new direction, etc., is called run and tumble motion. So these are, again, E. coli. They've had a meal. They're using the food that they consumed from the environment in order to self-propel themselves. And each degree of freedom, which is the E. coli bacteria, is an out of equilibrium component. After it became clear that active systems display a host of non-trivial phenomena that you can't find in equilibrium systems, people started developing a host of systems which are artificial active systems. And here I'm showing again a very old example from the Dave Pine group of self-propelled colloids. So these are again about a micron in size. They're hematite colloids. So it's a mixture of iron and oxygen. And they're covered with plastic. And there's one tip, you can see it here, which is exposed to the solution, which is hydrogen peroxide. And what I want to stress here, and that I wanted to stress also before, but didn't, is that these particles have a polarity. They're not spherical, symmetric. If I go back, if you look at an E. coli, it's clear that it has a direction in which it's moving. You can look at it and see its polarity. And similarly, these colloids have a polarity. So what happens at this tip is that when you shine UV light on the solution, there's a chemical reaction happening at the tip, and this chemical reaction starts to self-propel the colloids. So if I run the movie, initially the UV light is off. They're just doing Brownian motion. And you turn the light off, and you see that they start to self-propel themselves. The direction, of course, because of noise, is a bit random. So the direction diffuses about. And that's why people typically refer to these kinds of particles as active Brownian particles. So if you want to model these things, it's very straightforward. If I look at over-damped dynamics, we have that the velocity of the particle is controlled by external forces. So we have the thermal noise from the environment, which is typically negligible for the dynamics of these things. Then the particles are polar. They have an arrow associated with them, and they're self-propelled in the direction of this arrow. So U is the direction of the arrow. So in 2-dimension, cosine theta, sine theta, and V is the magnitude of the velocity. And the direction of the arrow is dictated by some random process, which you can specify depending on the specific model. And then you add interactions between the particles. So if you look at a single active particle, two very common models are inspired by what I showed you before, active Brownian particles. So these are the guys which move, but this arrow diffuses about. So if you look at them, they move run length, which is the velocity divided by the rotational diffusion coefficient. And after this length, they reorient. And on long time scales, it's very boring. They're just diffusing particles, nothing exciting happening. And you can either calculate this diffusion coefficient or guess from dimensional analysis. Run and tumbled particles, very similarly, they move in straight lines. And with a rate alpha, they choose a new direction. And again, this run length is just the velocity here divided by the rate at which they reorient. On long time scales, again, they're very, very boring. They just diffuse about, nothing exciting is happening. So low and boring. However, it was realized very quickly that once you let them interact either with external potential or with each other, they start to display a host of physical phenomena which are very different than what we know from equilibrium. And indeed, depending on the details of the interactions between them, for example, you can find many phases. The most famous is maybe the flocking phase of the Vichik model studied by Tony O'Toole, important contributions also by Ramaswamy. Active pneumatics, which display the low Reynolds number turbulence. And there's a whole zoo of interesting phenomena associated with these systems. So what I'm going to focus on this talk is what we call scalar active matter. I'm focusing on it because I like simple systems, and this is probably the simplest active system. And when we say scalar, it means that there's no coupling between the orientation. Can you see my image or only my can you see my face and my hands?
No.
Yeah, I can see your face and hand. Yeah, I can see your hand.
Oh, you can see it. Okay, good. So there's no coupling between the orientational degrees of freedom. Okay, so this means that there's these scalar active systems, there's no long-range order associated with the orientational degrees of freedom. So this is probably the simplest one. And despite that, it has an interesting non-trivial phase diagram. So the phase diagram for active matter, for this scalar active matter, takes the following form. If you go at dilute densities, or if you want low activity, The system is, as you would guess, homogeneous. Particles don't see each other. And if you measure a two-point correlation function, it decays exponentially with some characteristic length scale. When you increase the density, that's when active systems become interesting. You find out that the system undergoes something that looks very much like a textbook phase separation. So it goes under phase separation, it exhibits phase separation, and if you measure the two-point correlation function, it decays linearly with a scale that's dictated by the size of the macroscopic droplet, which grows with the system size. And the big surprise was that this system phase separates even if the active particles don't attract each other. So for example, in this movie, I'm showing you simulations of active particles which interact with each other only through hardcore interactions, and nonetheless they exhibit phase separation. So it's very tempting to think that this is just an extension of the usual phase separated state. However, if you take a system with, say, some attractive interactions, so that phase separates. So here I'm showing you numerics again of a system where V0 is equal to 0. It exhibits phase separation. And then I start cranking up the velocity of the active particles, cranking up V0. And you see that what the activity does, it initially destroys the phase separated state, going into a homogeneous state. But then as you crank up the activity more, you flow into what people call motility-induced phase separation. So I'm showing this movie just to stress that it really is a distinct phase from usual phase separation. And its physics has been studied extensively in the last almost 15 years. And it's understood that the instability that leads to MIPS is the fact that active particles, even when they collide with each other, then they slow each other down. And when active particles are moving slower, they tend to accumulate in those regions. So this mechanism was understood by Cates and Tayol. There's a nice review already from 2015 explaining the mechanism. And this is a movie showing that indeed active particles accumulate where they move slowly. So this is from the Roberto Di Leonardo lab in Rome. And what they do, they have a strain of bacteria which move slower where they're experiencing.
Maybe there is a lag. I don't see the movie. Maybe, I don't know, maybe
I haven't
my internet.
run it yet, so it's
Okay, sorry.
okay. So what they do is they have a strain of bacteria which slows down when it's subject to light, and what they do is they shine light and let the system relax to its steady state. And you can see that by shining different patterns of light, they can paint with the bacteria. And in fact, there are some people thinking about doing lithography using these methods. Okay, so again, this phase transition is understood very well. It's understood so well that for some specific models, we can calculate analytically the binodal. And I'm not going to talk about it in this talk, just to sketch the main idea. So what you do is you write down a continuity equation for the density. Because the polar degrees of freedom don't interact with each other, they decay very, very quickly. So the only slow mode in the system is the density. And then you write down a density much like you would do with model B dynamics. You have a mobility times a gradient of the chemical potential like quantity. There's another term that I'm not going to discuss, which doesn't matter for the discussion here. And the trick is that G, where in equilibrium it's equal to a derivative of a free energy, so that this is minimizing a free energy. Here we do a gradient expansion, but we allow G not to be a full derivative, a functional derivative of a free energy. And that actually gives a constraint on these coefficients. And introducing these field theories, you can actually these days derive them starting from specific microscopic models by some mean field approximations and gradient expansions. They were first postulated by in this paper phenomenologically, just by adding this KPZ-like term into a model B dynamics. And in fact, one can start with this equation of motion and remarkably build something that's the moral equivalent of a Maxwell construction, which is something that I did with colleagues, Alexander Solon, Mike Cage, Julian Taillot, a few years back, and you can see that it compares very, very favorably with the numerics, again, for specific models where we can derive the form of this equation. But once you have this equation, we have a well-defined formalism for calculating the binodals, and sort of the surprise is that by doing a smart change of variables, the system actually maps to an equilibrium system. Okay, so just to summarize my introduction, I've discussed scalar active matter. I've shown that even repulsive interaction leads to phase separation. This is something that's, again, been studied very extensively in the field of active matter, and it's called motility-induced phase separation. And I'm going to refer to it later as a benchmark. And many aspects are understood, and superficially, it's very similar to textbook phase.
I have a small question in the previous slide. So how did you get the form of the free energy, that is 0, and how do you know that this term will be physically relevant?
Sorry, could you repeat it, the question?
Oh, I'm saying that in the previous slides here you have given the form of 0 and
Zero. Okay,
0.
So I haven't written it down. You have to start with a microscopic model and derive it. And this you can typically get by a mean field calculation, starting from the microscopic model. And this guy you do by just keeping the lowest gradient expansion. Remember, we're not interested in the behavior at the critical point. We're actually interested in calculating the binodals far away from the critical point. It's more similar to a Maxwell construction than what you're thinking about with a critical point. Okay.
Okay, so that's why the whole description in the first equation, it is just more like a continuity equation. When we are trying to pose the whole problem by keeping all other currents aside, right?
Okay, so you just write the most, you could write it from symmetries, you could guess this guy just by symmetries. You would have a rho squared, a rho cubed, a rho to the fourth. But really, to calculate these guys, do this fit, you have to know more about this.
Okay. So, okay, thank you.
Okay, so this talk is not about that. This will just be a benchmark against which I'm going to test compare some of the things that I'm going to discuss. So I'm going to take scalar active matter. So we have interactions, for example, hardcore. And then we have our usual active dynamics, the thermal noise, and the active drive. And I'm going to add external disorder. And what I want to stress is that this is vanilla disorder. It's short-range correlated, it's bounded, it's derived from it's a conserving field, nothing funny. I'm not hiding anything in the disorder, meaning when I turn off the activity, my system relaxes back to an equilibrium system in the presence of potential disorder, which we understand for a very long time. And what I'm going to do is I'm going to ask two things. First, you subject an active system to bulk disorder, and you ask, how is the system affected? And then I'm going to do something even that superficially looks very silly. I'm going to subject the system to boundary disorder. So in equilibrium systems, boundary disorder doesn't do anything. It's I'm a bit exaggerating, but generally it's a sub-extensive correction to the free energy. It doesn't affect the phase diagram of the system. And what I'm going to show is that even in active systems, even this setup, which naively you would think is not important, shows very interesting behavior. Okay, so before telling you the results and how we derive them, I want to set the questions that we want to address. So we open a StatMech textbook and we ask, what can we ask about the disorder system? So the first question is, you have a dilute system, you add disorder, what happens to the dilute phase? The second question is, I have an ordered phase, for example, the phase separated state. I add disorder, is the phase stable against the presence of disorder? Namely, can I have phase separation in the presence of disorder? And just to remind you what we know about equilibrium systems, that's my model when the activity is 0. So when we have bulk disorder, then we know that the correlations, you put disorder and a disorder system, you expect the correlations to be short range. And indeed, it's a pretty simple calculation. You take a linear field theory, you add a quench disorder, you find out that the 2-point correlation in Fourier space is a Lorentzian squared, so correlations are short range. Then there's a very famous work from the 70s by Imri and Ma, which argued that the lower critical dimension, the dimension below which the system is unstable to disorder, is 2 dimensions for scalar order parameters. And specifically, in 2 dimensions, phase separation is destroyed in the presence of disorder. And the trick is basically comparing the contribution of disorder to the bulk of a domain to the surface tension. And that essentially balancing these things shows you which is more important. Then if I put boundary disorder on the system, so just take one boundary of the system, say a left one, and put disorder only along the boundary, then it's well known that nothing happens. It's a sub-extensive correction to the free energy. The free energy doesn't care at all about the boundary, so I can ignore it. So boundary disorder does nothing for the dilute phase or the existence of a long-range order. So in what the time that I have remaining, I'm going to show you that this is very, very different for active systems. For bulk disorder, I'm going to show, first of all, that the structure factor becomes scale-free even in the dilute phase. So we're used to having scale-free structures when we have interactions, for example, at critical points. And what I'm going to show that there's a very generic mechanism, very robust, for creating power law correlations, even in dilute phases with no interactions between the active particles. Then I'm going to show that the transition into phase separation is very sensitive to the presence of disorder. And I'm going to argue that the phase separation is not stable to disorder in dimensions 4 and below. So in any real experiment, asymptotically, we don't expect to see phase separation. And finally, because this is a non-equilibrium system, it can support currents. And I'm going to characterize the currents in the steady state. And I'm going to show that if you take a loop in the system, then the variance of the current along this loop grows with the length of the loop. So this is just to illustrate the difference between equilibrium and non-equilibrium systems. If you have an equilibrium system, which is phase separated, and you add disorder, the phase separation is destroyed, but the pattern is this short. If you look at and you measure the correlations, they're very short range, what you would expect. If you take an active system and you add disorder, you can see that you develop this fractal structure, which is actually, as I'll argue, is frozen up to some fluctuations in space. And again, it's a very, very robust mechanism for getting power law correlations in non-equilibrium systems.
So, sorry, Yariv, I have one question here. So, how do you characterize the disorder? It's a random thing or?
Yeah, just random short-range correlations bounded.
Oh, I see. Okay, I missed that probably. Okay, thanks.
Vanilla disorder like you would do usually.
Okay, thanks.
Okay,
And
So-
for any, sorry, I have one question. For any strength of the disorder, the phase separation goes away?
Yeah, so it's so asymptotically, yes, that's what I'm going to argue. Of course, for finite systems, you know, there's always a crossover, even in
Okay.
equilibrium.
Okay.
Okay, but asymptotically, yes.
Okay.
Okay, then I'm going to use the same tools that I'm going to introduce to study bulk boundary disorders. Again, this is disorder only along the boundary of the system. And if you look at a system with only boundary disorder, so this is a density plot. This is a plot of the density in the system. And if you look and you're not very careful, you see that there's some action along the boundary, but nothing exciting happening in the bulk. But actually, if you zoom in, you find that there are correlations which spread deep into the bulk of the system. And actually, I'm going to show that the correlations decay as their shape is a Lorentzian. So they decay in magnitude as a power law as you go away from the wall, but their extent grows with the distance from the wall. Similarly, if you look at the currents, right, it's a non-equilibrium system, it can support currents. So here I'm plotting the current in the y direction. And if you don't look too carefully, you see that there's currents next to the boundary. But if you zoom in and look more carefully, something's stuck. Okay, here. Oops, sorry. If you zoom in, you notice that actually the boundary is creating eddies in the system, and the magnitude of the eddies decays with the distance from the wall, but they spread wider and wider as you move away from the wall. And most striking is the fact that even though these effects decay into the boundary, you can ask what's the fate of the phase-separated state here, a state which is wetting the wall. And what I'm going to argue that in dimensions 3 and below, boundary disorder alone ruins the phase-separated state. So boundary disorder completely alters the phase diagram of the system. And this is just an illustration of what's happening. So this is again an equilibrium system, which is phase-separated. We add boundary disorder, which is repulsive here, just to make it more dramatic. So it's a repulsive disorder. And you see that if you look carefully, it's a bit depleted next to the boundary, but it's still, as you would expect, phase-separated. Boundaries don't affect the system. However, if you take an active system and you turn on the boundary disorder, then the phase separation is destroyed, and sort of the particles aggregate in these clumps next to the wall, which are broken, and we understand how to characterize these clumps why these clumps result, as I'll explain later in the talk. So this is really important.
I have a question.
Yes?
I have a question. This active disordered wall, this slide that you have, they don't look to me like completely disordered. It's not, I mean, I can still see some patches. So is it possible that, I mean, you just have more fluctuations, but actually it is possible to have some long range order, or it is absolutely ruled out that it doesn't?
No, it's ruled out. It's ruled out, and we understand why these patches have the statistics that they have. Okay, so these patches are of finite extent, and hopefully by the end of the talk, you'll have a feeling for why they look like they do.
So even if you scale up the system size, the typical size of the patch does not scale with it?
Yes,
okay,
exactly.
Okay. Thanks.
And the correlations in the bulk are like in the disordered phase. Okay, like in a dilute system.
And even if you crank up the activity, or let's say the density, you never get it back.
Yeah, never.
Okay.
Yeah.
Okay.
I'll try. Hopefully, I'll get to it.
Okay.
At least you'll see the techniques that I use. Okay, so this is to us very important because this means that you can't ignore boundaries in active systems. Okay, so typically when people study active systems, they look at periodic systems or infinite systems, and this result implies that boundaries can have a dramatic effect on active systems. Okay, So now I've shown you all my cards, you know the results, and I want to argue for how we get these results. And what I'm going to show you is a methodology that we've developed to tackle disorder in active systems. It's a bit more subtle than what people usually do, but I'll try to explain it slowly, at least for bulk disorder. So what I'm going to do to study bulk disorder first, and as I'm going to first look at one defect, one small speck of disorder inside an infinite system. So to localize generally ugly looking piece of bump of potential disorder inside an infinite system. Then I'm going to use this result to study dilute systems. And then I'm going to use both these insights to say something about interacting systems. And once you understand the method that I've developed here, I'm going to apply it again for boundary disorder and derive all the results that I've mentioned before. Okay, so bulk disorder, and again, you can find all the details in this manuscript. Okay, so again, as I said, the first thing I want to look at is one amorphous piece of potential inside an active system. So when I throw something, it's not going to look like a sphere. It's a general clump of disorder. And I've drawn it in this way just to make my discussion easier. As long as it's asymmetric, nothing is going to change. So we have an active system, and then we have this asymmetric potential in the middle. And we know for a very long time in non-equilibrium statistical mechanics that once we break time reversal symmetry and we couple this to a breaking of a spatial symmetry, here this asymmetric potential, it's really easy to generate currents. This is ratchet currents. So ratchet tells us that we have a non-equilibrium system, you have a spatial asymmetry, then you have a ratchet. And these systems, and for this potential, it's really easy to understand. If I have a particle with an arrow pointing to the left, it moves, hits the potential, slides, and moves to the left. If I have a particle coming from the right, it gets stuck here, accumulates here, and pushes against the potential. So we expect a current from right to left. There's another neat way of thinking about it. Because the particles accumulate here and slide when they come from the right, then the active particles are exerting a net force on the potential inside the system. By Newton's third law, this potential is reacting back and exerting a force on the active fluid. So if I look at an active fluid which has one localized asymmetric piece of potential inside, it's exerting a force on the active particles. So if I look in the far field, I can sort of guess what's going on. The bump is pushing the particles, essentially acting like a pump. These particles are diffusing on large length scales. Remember, that's why what I showed you. These particles on large length scales are essentially diffusing. So I put it in diffusion of particles, and then I put in a pump, and the pump is located in the origin. That's where my speck of disorder is. So again, the physics of this is just that an asymmetric potential is acting like a pump. It's exerting a force on a diffusive fluid. This is an equation that we know how to solve from electrostatics. So the density of particles here in 2 dimensions behaves like a potential of an electric dipole. So it decays like a power law as you move away from the pump. It's anisotropic, and it's anisotropic, as you might expect, because it's a pump that's pushing particles from one side to the other. And the current is, again, it's diffusive, so you act with a gradient and use the diffusion coefficient, and it's what you would guess. You're pushing the particles in the center, and they're going to look like the field of an electric dipole. Okay? So the important point of this simple argument is that if you have a potential, unless it's spherically symmetric inside an active system, then in striking contrast to what you have in equilibrium, where The potential is only disturbing a correlation length away from it, the density profile. Here, it's causing a power law modulation in the whole system. And so it causes long-range density and current fields because of the asymmetric potential. And that means that specifically, if I would write down the steady state, it would be a non-local function of the potential, even for dilute particles. So you can generalize this to any dimension. And again, the bottom line is that an asymmetric potential acts like a pump. And you get that, again, it decays like a power law, a dimensional dependent one. And again, I've only sketched the derivation here. We can actually start from microscopic equations and build up the multipole expansion and derive these results. And we can do it both for non-interacting particles that was initially done here, but actually we were able, Omer Granek, which is a PhD student here, was able to actually generalize the calculation even when you have pairwise interactions between the active particles, which is a non-trivial calculation. As a side note, I want to say that so far I've discussed an asymmetric potential inside an active fluid. I said that it's like a pump inside a diffusing system. And that led us to study a pump in a critical system. And we've just posted this a few weeks back. It's a different topic. I won't talk about it, but if you're interested, you can find the paper here. Okay, so now, again, asymmetric potential leads to this long wavelength, this long power law disturbance in the system. So I'm going to use that now to study a disordered system. So I take my disordered system. So again, the idea is that we have my active particles, which are interacting with some external noise, the active drive, and my disordered potential, which again is vanilla, short range, bounded, nothing special about it. And what I'm going to do is I'm going to use the previous result to analyze the dilute limit. So I put a bit of disorder in the system, it acts like a pump. I put more disorder in the system, it acts like another pump pointing in another direction. I put another speck of disorder, and each of these specks is acting as a pump in a random direction, which depends on the microscopic realization of the disorder. Before proceeding, I want to say that this means that the particles experience a random force by the pumps, which is pushing them in different directions. And in fact, random forcing has been studied a lot in the 80s already as a simple model for dynamics in disordered systems. And there's beautiful work by Bernard Derrida, Daniel Fisher, and there already in 1990, there was a very nice review by Jean-Philippe Bouchot, Pierre Ledoussal, and others, which reviewed the physics. However, these were for single particle systems, and here the active system, the notion of active systems sort of brought up the interest in the many-body generalization of that problem. Okay, so I take my result for an asymmetric potential now localized at R prime, and what I'm going to do is I'm going to assume that I have a random this field of dipoles is just randomly distributed in space. So again, the physical insight is that a random disordered potential translates into a pump, which is very different than equilibrium systems. And I'm going to draw these pumps from a random distribution. Slightly sloppy here because this is a force and this is a force density. Doesn't matter. You do the calculation and you find out that the structure factor is 1/q squared. So it's a power law. And note that this is even in the dilute system. These pumps are pushing the particles in specific locations, creating the scale-free structure. So this is a simulation of what's happening. So we start with a disorder, we let it run, and you can see that it's evolving into the scale-free structure. It's fluctuating, but if you note, they're localized in specific locations in space. So the pumps are sort of directing the particles to stay in specific locations in space. And what I'm showing below here is just a confirmation that indeed in 2 dimensions, the 1 over q squared translates into logarithmic correlations, and we indeed verify this simple theory using numerics. Okay, so just to recap, dilute system, you put in this order, you get these power law correlations, and now I'm interested to ask, what do interactions do? Do they modify this? And can I ask something? Can I get
Hello,
insight?
can I ask a question?
Sure, of course.
In the previous slide, where you introduced the concept of pump,
This one or before?
the slide hasn't come up here.
Yeah, there is a bit of delay. I don't know from
sorry.
which side. Yeah.
So which slide? You have to be more specific.
Okay. So it's the second before slide. Yeah.
Oh, the
2 slides before.
Last 2 slides. Yeah.
this
Second
one.
last. So my question is, can the pump push a particle? I mean, if opposite of its orientation direction. I mean,
So
if you
again,
consider an yeah.
So what happens is that on average, what the pump is doing is causing the particles. Okay, let me go back and show you this movie. Not the movie, sorry. Sorry. Just let me know.
I think structures are frozen somehow.
Okay, let me know when you can see. So now I am in this one localized deformation.
No, actually nothing is moving, Yariv.
Yeah,
We
yeah.
are stuck on the same slide.
Which slide?
Maybe you can stop presenting and then again reshare it.
Okay. Okay, let me stop presenting. Okay, sorry. Okay. Can you see it now?
Yes.
Yeah.
Okay, so back to your question, if you look at what's happening, if you have a particle that's hitting this potential, then what you notice that essentially it's being polarized by the potential. Okay, on average, of course, it's being polarized by the potential. So if you look far away from the pump, and actually the polarization is actually related to the current, then it's actually effectively what this pump is doing is polarizing these guys in its vicinity. Because if it comes, it slides and it's polarized in this direction. Here it comes, it's stuck, and it reorients, and it comes out, it's also pointing to the left edge. Okay, so that's something that's well known in active systems, that potentials tend to polarize the active particles.
I want to ask one question, Yariv.
Sure.
Yeah, so this is regarding this polarization of particles. So whatever the structure factor you are showing, that is the density structure factor, I guess.
Yes.
What about the velocity or the orientation correlations with the disorder?
In this system, it's in this system it's not very interesting because they reorient much quicker. Okay. There are correlations, they're much weaker because roughly speaking, the polarization goes like the gradient of the density.
Okay.
Okay.
Thank you.
So they're less interesting.
Okay, thank you.
Okay. Okay, other questions? Okay, so now I'm going to turn into interacting systems. And the approach will be to write down the simplest linear theory that we can imagine to describe this thing. And then I'm going to check when it's self-consistent. And sometimes you're lucky and you're self-consistent within the linear theory. So I want to write down a field theoretical treatment for the disordered problem. So again, I have my conservation equation for the phi, which is the deviation from the mean density here. And I start with the current, which is the simplest gradient of a chemical potential, what you know from the usual stat mech book. It's just a linear gradient of the simplest linear chemical potential that you could imagine. Remember, all the activity came at the nonlinear term. And then I'm going to add the disordered potential. And the crucial point is that instead of putting a potential in the free energy and then writing down this disorder as a contribution to mu, we know that on large length scales, it actually translates to a forcing term. And that gives very, very different physics. I'm stressing this because I've seen some papers where they do the opposite. And then we take this forcing term and we draw it from a quenched random Gaussian distribution, which is uncorrelated in space. Okay, so this is a simple enough field theory. I can add to it, just random noise from thermal or whatever origin you want. General, this shouldn't be thermal, so it's some Gaussian noise from the dynamics. And you can look and calculate the two-point correlation function. It's a linear theory, so everything's very simple. And you find out this expression. And importantly, in the small q limit, I recover exactly the result of the dilute picture. So this means that the interactions which are encoded in this k actually lead to higher order corrections to the correlation function. So there's also a component in u, but anyway, so sorry, I wasn't very clear. At the end of the day, the important point that in the small q limit, you go into 1 over q squared. So it's natural to ask, why does this field theory give me a 1 over q squared correlations? And there's actually a neat way to see this. And to do this, what we do is use a Helmholtz decomposition. So I write down my field theory. So I remind you, I have my time derivative of the density is minus the divergence of the current. And I have this current, which is just this linear field theory terms plus this random forcing. And what I do is I take this random forcing term and it's a vector, and I decompose it using a Helmholtz decomposition. And now the trick is that this guy has a divergence which is 0, so it doesn't contribute to the dynamics of phi. So as far as phi is concerned, this guy is non-existent. The current, of course, is affected by this guy. But as far as phi is concerned, this guy doesn't exist. So I'm left with an effective equilibrium theory, but now with this potential whose statistics I can extract from the statistics of the random forcing. So you can do that. That's a straightforward exercise. And you find out that the two-point correlation of the random potential in Q space is 1 over Q squared. So essentially, what we have is that these pumps are creating a potential which is Gaussian surface. It's self-affine, and I look at larger and larger scales on this surface. I'm seeing wells which are deeper and deeper and deeper, and they're essentially just accumulating the particles inside these wells. So again, the pumps are creating this self-similar structure, and the particles, even without interactions, are just falling into these traps. You can check if the theory is self-consistent, and that, again, you just check when the fluctuations are small. And what we find out is that in 2 dimensions, we expect the theory eventually to break down beyond a length scale. However, this length scale is exponential in the parameters of the model. And despite really, it wasn't me, but the team here did heroic efforts numerically to try and find something funny, and they really couldn't find anything beyond the log correlations, and they really, too much. The carbon footprint of the effort was too large. And then you can check for higher dimensions, and we find out that for dimensions larger than 2, For weak disorder, the theory is self-consistent. However, for strong disorder, there could be a new phase, which we don't know anything about.
Yari,
Yes.
so how does activity enter here?
So the important part of the activity in this work, in this theory, is that, let me go back, is that typically when you had a random potential, you add a term which is the potential here. Okay, so there's a gradient of the potential. However, here, using the insights from before, instead of just having a random potential, the activity translates the random potential into a random forcing. So the random potential acts like a pump. So the fact that I put here these random
Oh, I see.
is the important ingredients. I could get exactly this.
Oh, I see. So you are putting current by hand, sort of.
Well, using the
Disorder current, current operator.
Yeah, not really by hand, a bit better than that, but
Yeah, by hand is not the right word, but yeah.
yes.
Yeah.
But
Okay.
you're using the insights from before to get this
Pumps. Disorder pumps.
Now we're actually deriving these field theories in a more organized way. But the crucial thing is that when you see a random potential in an active system, don't put a random potential, put a random pump.
Right. Okay, thanks.
Okay, let me run forward. Okay, so next thing, you could look at the currents inside the system, and again, it's a straightforward calculation with the sphere theory. Now that you understand that essentially you have random forcing, random pumps kicking it in different direction, then by central limit theorem, if you have a loop of length c, you expect the current whose variance grows with c, and this is indeed what we see from the numerics also. Okay, the last thing you could do is ask how stable is long range order to this thing. So you have now the disordered potential. You do your run-of-the-mill Imrima argument, because remember, the linear order, it looks like an equilibrium theory with a funny random potential, and you find out that the lower critical dimension is 4, meaning that there's no phase separation below 4 dimensions. And here I'm just concluding this part by showing a movie where you have active particles and you crank up the disorder, and you see that you go from this phase separated state into this self-affine fractal structure. Okay, how much time do I have?
Another 10 minutes.
10 minutes. Okay, so
Yeah.
I'll just guide you. I'll just guide you very, very quickly through the boundary disorder. And again, you can find more details here. So the approach is exactly what I described before. We start by looking at one localized potential disformation, but now we put a bump next to the wall. So we take a wall and we put a small potential bump on the wall, which is generally asymmetric. And technically, it's harder because, anyway, the technical reason is that these theories, you can't use neither Dirichlet boundary conditions or Neumann boundary conditions. So you have to be a bit more creative, but you can actually solve it, and you get the result that you might guess without doing anything. You find out that this small bump acts like a pump, but the pump is now parallel to the direction of the wall. Okay, so this is what's encoded in this. So the pump is parallel to the wall, and then the density modulations are essentially just, again, parallel, anisotropic. The pump is pushing particles from the bottom to the top, so you have more particles here and less particles here, and because it's pushing it, we have currents which are flowing, again, like fields of the dipole, with the dipole which is parallel to the wall. And again, we can do this both for dilute systems and with pairwise interactions. Now we take the same idea and model a dilute system by just random pumps along the wall. So a disordered potential is just random pumps which are oriented along the wall. And what you find out using, again, the same approach, that the 2-point correlation function is a Lorentzian. It decays with the distance from the wall, as 1 over the distance from the wall, roughly, but it spreads more as you move further in the perpendicular directions, as you move further and further away from the wall. So this is for equal values of x and different values of r parallel to the wall. And you can see the theory with our calculation, and it works beautifully. And this is, again, just to collapse, to show that everything collapsed as expected. And really, the picture is that now the wall, you see, before we had the disorder steering the fluid, and now we have steering which is confined to the wall. And you can use the, okay, and this is a comment I want to add, that actually for this whole effect to propagate into the bulk of the system, you actually have to have a disordered system. If you have a periodic system, you can show that the effects of the boundary are screened on a length scale which is comparable to the length of the period of the disorder. Okay, you can do the same thing for the currents, again, the same theory, and you find out that the current has, so at a distance x from the wall, the scale of the eddies which are created by the wall is x, and you can see that again they decay in scale, but their magnitude is growing. And again, now that we have the dilute system, we do the same trick as before. We take our linear field theory. We now add disorder, but now the disorder is only confined along the wall. Same idea as before. You do the linear theory with this now disorder along the boundary, and you do the calculation. You find out that the structure factor agrees with what we had before. You can check when the theory is self-consistent. This time we have to do just, the usual scaling to check which terms are important on large length scales. And we find out that the theory is good for any dimension larger than 1. And again, we draw this effective potential, and you find out that this effective potential has the statistics of this Lorentzian. So this goes back to Shakuntala's question from the beginning. So what's happening is that near the wall, okay, let me go to the figure. So near the wall, we have this effective potential which has large valleys and bumps along the wall, and essentially this potential is attracting these particles to fall inside these wells, but they're of finite extent. That's essentially the physics of the picture that you saw before. Okay, because I'm sort of running late and I want to leave a few minutes for questions, you can do a Imri-Mal argument for the stability of the phase separation in the presence of the wall. We do it in the paper in 2 ways. There's a neat way that's based on an old paper by Meran, where you calculate the roughness exponent of the interface. And at the end of the day, we find out that below 3 dimension, this system is unstable towards disorder. And just to summarize, this is a phase separated system which wets the wall. We add disorder along the boundary, and you can see that again, you create these clumps. And more important, if you go into the bulk of the system and you measure the 2-point correlation, you get exactly the result that we calculate for the dilute system. This is, again, a movie similar to what I've shown before. We have a phase-separated system. We put disorder along the walls. And what you can see, and again, just disorder along the walls, that the phase separation is destroyed, and you get these clumps. And again, the interpretation is that we have this effective potential, which becomes deeper and higher near the wall and decays in magnitude, but that's enough to sort of break below 3 dimensions, break the domains, and destroy the long-range order. So just to summarize, maybe the most important point of this thing is that this order, or effectively any asymmetric potential, essentially what it does, it steers steers the active system. You just can't treat it in field theories, etc., as an external potential. You have to put in the fact that it's pushing the active fluid. This leads to generic long-range correlations, which I think is a new mechanism for generating long-range correlations, even for dilute systems. And again, this means that the results hold for any dilute active system. So whatever theory of whatever active system you do in the dilute limit, it better agree with what we've done. The lower critical dimension for motility-induced phase separation is 4 for bulk disorder, and it's 3 for boundary disorder, which again, to me, this is a much more striking result because it means that you can't ignore boundaries in active systems. You really have to worry about the specific boundaries that you have. They can actually modify the phase diagram. And finally, there's a bunch of stuff that we've done on the one-dimensional system, which is summarized in this paper from 2 years back, that you can look at or ask me now. So thank you again for your time, and I'm happy to take questions.
Okay, thanks Yariv for your nice talk. So now it's open for questions. So if you have more questions, so please feel free to ask.
Hello.
Hi.
I have a question. Okay.
Yeah.
So you just showed that the phase separation is destroyed by the introduction of disorder, right?
Yeah.
So can one understand this from the microscopic point of view? Like, if there is no disorder, then there is, in the case of say random particles, so there is a trapping event occurs. So and how the disorder plays a role? I mean, here, yeah.
So again, on the microscopic scale, the important physics is that the disorder is, it's like somebody mixing up the active fluid, but in random ways. So you see, you're making soup, and you have hundreds of little spoons, each stirring it in a different direction. So you can imagine that it's very hard to maintain a phase-separated state. Just take sand and start mixing it. It would spread everywhere. So that's the essential physics that we have here.
I see. Okay.
Sir, can you go to the conclusion slide?
To which one?
Sir, conclusion. Yes, summary, sir. Sir, what is the means of the lower critical dimension for MIPAC DC is equal to 3? Because I studied many papers in that the dimension 2, in that case we also found that MIPS cannot understand that DC is equal to 3, lower critical dimension. Can you
again, to actually do this, you have to go through the Imri-Ma argument. So essentially the idea is that you have an energy for the surface. Remember, it's an equilibrium system within the linear theory. So you have a surface energy, and then you have an energy of the bulk of this and then you're interested in the energy of this interface. So what you do is you just do a rescaling. So you rescale the coordinates, and then the slab width increases, and you take an exponent zeta for how the width of the interface grows. And then you essentially what you're doing is you check how does the elastic energy change under the rescaling. How does this interface energy change under the rescaling? And you balance them to get the roughness exponent of this interface. Because what determines this exponent is the balancing of these two energy between the external disordered potential and the surface energy. And then the trick is that when this roughness exponent becomes larger than 1, this interface can't be stable because it means that it's growing faster than the width of the interface. So that's essentially the argument leading to the 3 dimensions. Okay, and there's another argument that you could do by assuming a droplet in the bulk of the system which you can find in our paper. It's a very similar imrima. You calculate the surface energy, you calculate the energy of a droplet that's somewhere inside the system, you look at the variance of the energy, and you see who wins asymptotically, the surface tension or the bulk disorder.
Okay. Any other questions?
Okay, I have a question.
Yeah, please go ahead.
Okay. So you have shown that the particular effect of disorder in active system is a kind of a pump-like phenomena, forcing introduced in the system. So, so is it similar for any kind of disorder that I introduce in the system?
For equilibrium, no.
No, not in equilibrium. In active systems.
Yeah. So we've also looked at the disorder in torques. And that does a very, very similar thing. So if you allow for torques, it does exactly the same thing. So the short answer is, okay, sorry, I'm just recapping. If you have disorder only in the velocity of the active particles, then the answer, strictly speaking, for non-interacting particles is no. Okay, but once you have disorder in the speed of the active particles and you add interactions, then the answer is again yes. Okay, so I give you probably an answer that's more complicated than what you wanted.
Okay, I somewhat thinking that the strength of the disorder must have some coupling with the velocity of the active particle, velocity of the active particle. Because if I introduce a very weak disorder or something that is not affecting the particles, then I shouldn't see any kind of phase separation or the breakdown of phase separation in the interacting regime.
So again, asymptotically, our arguments are sound. Going back to your question, let me just get to the correct slide that will illustrate this. So if you look at this result, then you notice that the modulation of the density depends on this effective diffusion coefficient, which is proportional to V squared over alpha, or the rotational diffusion coefficient. So definitely the activity enters here.
Okay.
So the details of how strong the random forcing is depend on the activity.
Okay, thanks.
Any other questions from anybody? Okay, if not, here I have one. I just remember one paper by I think Lebovic and Derrida. So they also studied similar system like pump in a symmetric exclusion process. Can you comment on that? I mean, what are the similarities of that work to your works?
Okay, so that you would have to go to one dimension.
Right, yes.
And in fact, probably a better analogy. So if you look at a pump in a diffusive system, there's a paper which is almost 10 years old by Tridib, Satya, and David Mukammel, where they look at a driven bond in a diffusive system, and the behavior is exactly the same.
I see.
As an asymmetric object in an active system. And sort of talking with David, we came up with this question of what happens to a pump in a critical system. Right. That's what this new paper is about.
Okay.
The details in the archive.
Right. Okay, thanks. Anybody else? Okay, so if not, let us thank the speaker again for a nice talk. And Yariv, thanks for agreeing to give a talk here.
Okay, my pleasure.
So thank you. So let us keep in touch. So it's an interesting talk. Yeah. Yeah.
Okay.
Okay.
Bye-bye.
Have a nice time. Bye bye.
Bye.
Bye.